We have talked at the very beginning of the semester about properties of liquids and solids, and so we're going to review that a little bit here. We spent an entire chapter talking about gases. We talked about how in gases the molecules or particles are separated by large distances, and we said there's essentially no interaction between them, and that's because of the large distances. But in a solid or a liquid, the molecules or atoms are what some books call touchingly close. So they're much closer to each other. And so the molecules are much closer, and those intermolecular forces do depend on distance, kind of like magnetic attractions do. If you have two magnets and you hold them at arm's length, you don't feel any attraction between them. And the closer you get, when you get them really close, then you feel, oh, there's this strong attraction between the magnets. So in a liquid and a solid, the particles are held close together because of those intermolecular forces. What's the difference between a liquid and a solid? They both have close particles. Well, in a liquid, the particles are able to move relative to each other, and in a solid, they're fixed. They're still moving, but they're fixed relative to each other. So here's an illustration. Here we've got the gas. The particles are widely spaced, and they're just kind of going their own way, and they're not interacting with each other at all. In a liquid, the particles are close together, but they can move around. In a solid, they're arranged in a particular order, and they stay however they are, and they just wiggle. So this is like, students sitting in neat rows, which we don't have in this classroom, but some classrooms do, sitting in neat rows, and they just stay there. And here they're just milling about. So this is like during lab when we're getting up and getting stuff and we're all milling about, but we're still within arm's reach of each other. So gases have very low densities because of that large amount of empty space between the particles. They have indefinite shape, so they will take on whatever shape their container is. And they have indefinite volume, which, since we can't usually see gases, is something that's a little hard to fathom. But a gas will expand to fill whatever container you put it in. And that also means it can be compressed. So you can make the container smaller and the gas gets smaller. That's not true of liquids and solids. They have very weak intermolecular forces relative to thermal energy. An example is carbon dioxide gas. Liquids have much higher densities because the particles are so close together. They also have indefinite shape. They will take on the shape of their container, and you can demonstrate that at home with water. You can pour it into a tall, skinny glass or into a wide, shallow baking dish, and it will change its shape, won't it? But it will not change its volume. It might look like more or less, but the volume stays the same regardless of whether you have it in a small container or a large container. Liquids have moderate intermolecular forces, and an example is water. Solids also have high densities in the same realm as the liquids. They're roughly the same. But solids have definite shapes. They don't take on the shape of their container. You can move a solid from one container to another, and it keeps its shape. It also keeps its volume. And you can't compress them. You can't compress liquids either. There were two basic types of solids. We talked about these earlier as well, crystalline or amorphous. A crystalline solid, the particles are in some sort of an order that is long-ranging. So over the whole chunk of it, if you looked, you could see an order to the particles. There's different ways they can be ordered, but they'll have a specific order. Amorphous means without shape. And so in an amorphous solid, such as rubber or glass, the particles are not arranged in any particular way. But because it's a solid, they're still fixed relative to each other. So if we used students as atoms and looked at the solid that we are right now, we would say this is an amorphous solid because we're not really arranged very neatly. If we were all sitting in rows, then it would be a crystalline solid. So solids have strong intermolecular forces. An example is sugar. Yeah, I edited these slides, but I didn't write these slides. And so they're kind of belaboring this point. I think it's a little silly. There's an illustration, liquids milling about. Solids with the definite shape. This is a picture of ice. In fact, I think that might be an iceberg. I'm not positive. But ice is a crystalline solid, and you can see that these water molecules are making particular order in here, and there's a pattern to them that's crystalline. Enough of that.